Okay, why don't we get started then? So welcome everybody to the week 4 discussion. I know a lot of you are, definitely a lot of folks who are taking the independent project are also participating in the more standard BWorks courses. And to that point, not expecting a little bit smaller attendance, but that's okay. These are all recorded, so they'll be able to watch. You'll be able to watch. So just as a sort of a disclaimer, in addition to the more explicit disclaimer I'm about to give, this is going to be a fairly sort of compressed, dense discussion / lecture, and so I'm sure this will generate a lot of questions and whatnot. So I'm trying to keep that part kind of short so we can get to the questions. But let's dive right in. Okay. Sorry, just give me 1 second. Computer is being. All right. And I'm going to go and share screen. I hope everyone can see the PDF. Okay. So we're going to talk about detection theory. And that's maybe a little bit of a misnomer, maybe a little bit of a red herring in the sense that there's this topic comes with a huge disclaimer that the topic of detection theory is entirely too broad. I'm missing a word. Entirely too broad and too deep to address in 1 hour. Okay, I personally have taken at least 3 or 4 undergraduate, graduate courses dedicated to this topic alone. So we are not going to really get very deep into it at all. We are just going to introduce some very basic fundamentals, explanation of how this concept could apply to PACT, and then give you some recommendations of how they may apply to PiPact. You all are expected to do your own research when it comes to getting to a sufficient understanding to determine if you want to apply detection theory to a project. Not only if you want to apply it, but how to apply it. But we'll try to help you along. So let's start with the very basics, and there are a lot of very basics. So let's start with what is detection theory? So it's kind of simple. Basically, given a measured signal, and signal can mean basically anything. It doesn't have to be a 1D signal. It can be 2D, it can be 3D, it can be whatever dimensionality signal you want. So whether it be audio, images, video, all sorts of signals are applicable. But the bottom line is there is a signal of interest that we want to detect or declare its presence or non-presence. And we call that signal the signal of interest. And usually the signal of interest is associated with some known phenomena or identity. And this refers to the fact that when that phenomena or identity occurs or manifests, the signal in turn occurs or manifests. And therefore, by correlating those two things, we can declare whether that phenomena or identity has occurred. Okay. So some examples, or some very basic examples, is smoke detection or fire alarm, right? That smoke detector on your ceiling, it is actually doing some very basic detection theory by virtue of its goal is to detect the signal of fire or smoke, right? That's the phenomena it wants to correlate with the signal it's measuring. We ourselves, right? We do a lot of signal or detection theory. For example, finding a certain person's voice in a crowd, or defibrillators, right? I don't know if any of you are familiar with those, but they actually do some detection theory where they actually won't activate if they don't detect an irregular heartbeat. After all, you don't really want to be shocking somebody whose heart is doing just fine. Cancer detection, face recognition, your iPhones, your Androids, when they do the face recognition, it's actually a detection theory application in the sense that they're trying to detect a particular face, particularly your face. And then what I do for my day job, detecting airplanes with radars, for example, right? The goal there is in the radar signal, you want to detect whether there's an airplane or there's not. Now, what are some challenges associated with this? Well, probably the most common challenge is that the signal of interest may be obscured or hidden, basically corrupted by noise, which I'll show some examples on the right shortly. And also that the signal of interest does not have just one manifestation. It does not present itself in only one way. So a good example is your face, right? Your face can present itself in multiple, poses in terms of angles, lighting, your expression, whether, maybe you have facial hair or you don't, glasses, no glasses, so on and so forth. But they're all correlated to the same underlying identity. So they're all the same, they all qualify as a signal of interest. So you can see here on the right, I'm showing just basically those two broad categories where the left column is where their signals are present, and the right column is where signals are not present. And it's pretty obvious in the first two rows that the signal present is this large peak, right? And there's some variation between them in terms of its position in time, which is the x-axis, and also its relative strength. However, down on the last row, you can see this is the signal of interest, but it's very weak in comparison to the other signals of interest, and it may actually be considered somewhat challenging to declare that this is actually a signal. Over on the right is nothing but noise. This is just noise. And so here, the challenge is saying that the things in the left column are all signals of interest, while the things in the right column are not signals of interest, or the signal is not present. And it's this variation and sort of corruption by noise that are some of the most common challenges associated with detection theory. All right. So the next topic to introduce is what we call the observation model. And this is a model that attempts to parametrically, in other words, with a formula, with an equation, tries to capture how the ideal signal of interest, the perfect signal of interest, is actually measured in the presence of real world effects, right? So we may know that there's a perfect version of the signal, an ideal version of the signal, but because we're actually doing things in the real world, we'll never get that perfect signal. So how do we, the way we model that sort of imperfection is called the observation model, and it can sometimes be very simple and sometimes be extremely complex. People dedicate their lives to coming up with accurate models for signals. The relationship between the measured signal and the ideal signal. And so the simplest version of this sort of observation model is what we call signal plus statistical noise. Basically that the signal is corrupted by some sort of random noise that can be modeled parametrically. For example, additive white Gaussian noise, all right? And so for example, here is just an illustration that, our ideal signal is just a single, it's zeros everywhere except for this non-zero value at some position. And then when we add noise to it, it obviously makes the measured signal look different than the ideal signal of interest. They still, you can still tell there's a signal in here, but it doesn't perfectly match for obvious reasons. So the relationship to what we're doing in the PiPact is that the ideal signal we're trying to detect is this Bluetooth beacon advertisement, right? That declare, that should just be a, look almost like this ideal signal of interest from a RSSI perspective. But, we've got different types of noise. We've got fading. We've got obstructions. We've got orientation of the devices. So the measured signal we actually see is very different than that ideal signal. So, we kind of need to have some idea what the observation model is. Now to some more pure math, density and distribution functions. So some of you may have already had some of these concepts in maybe some more advanced math classes. But basically, density and distribution functions are functions of random variables. And so random variables, right, they're variables that who take on values based on randomness. I know it's a little bit circular logic, but the idea here is every time we observe this variable, it has a likelihood or a probability of assuming a certain value. And what that likelihood or probability is depends on the nature of the variable. And so the way we capture this randomness or variability is with these two functions: probability density function and cumulative distribution function, or PDF and CDF respectively. The PDF describes the relative likelihood or probability that when we observe the variable at any given time, that variable has a value equal to a certain value. And so over here on the right in the top row, these are normal distributions, normal or Gaussian distributions with different parameters. And basically what it's saying on the x-axis is this is the value the random variable takes. And on the y-axis is the relative likelihood that the variable takes that value. So the mean of the distribution, or the average of the distribution, which is this peak here, is the most likely value, while the values that have lower probability are less likely. All right, and we'll get into why this is important, but it's important for you to understand that this is how we model random variables. Now, the cumulative distribution function is related to the PDF in that all it is the integration of the PDF, or the summation of the PDF along the random variable value. And all it describes is the likelihood or the probability that the value that a given variable takes is less than or equal to a certain value. So this has a one-to-one correspondence. The green curve is the CDF. This green curve is the CDF for this same green curve for the PDF. And you can see here that on the left side of the distribution, where there's values that don't have very high likelihood, the CDF says that the likelihood that a value will be one of these values or less is relatively small. But as we get into more values that are more likely to occur, you can see the CDF starting to rise, because this is where values are likely to occur, and therefore you're likely to have a value less than or equal to that value of the CDF. And then as we sort of fall off this and get into less likely, the curve of the CDF shallows out, because now we're observing everything. As you can see here, the shape of these curves sort of tell you where the density of the function is. Now, both of these functions can be modeled either parametrically, i.e. by a closed form formula. And if you look up on Wikipedia or whatever, you'll find closed form versions of both the PDF and the CDF for normal distributions. But we can also empirically measure them, and we'll show you how that does later. But basically, you're just observing that random variable numerous times and counting how many times a value occurs, and that becomes the likelihood of it occurring. All right. So now that I led into that, the empirical part of it. Hold on, there's a question here For the PDF of normal distributions, what numbers are set by the different lines and how do these affect how the line looks? A good question. So for a normal distribution, it's entirely defined by two parameters. The mean, mu, which is this set of values here, and the variance or standard deviation, variance being standard deviation squared. And so the mean tells you what is the most likely value. That's where the peak of this curve is. And the variance tells you how broad this hump is. The higher variance, right? So for example, this orange line has a variance of 5 compared to the blue line, which has a variance of 0.2. The values away from the mean are more likely. This basically tells you the spread of the values, right? So the smaller variances, the narrower or more concentrated the distribution of values is, versus the larger the variances, the wider, far more spread the values are. The mean just shifts where the peak occurs. And this will be better illustrated with the actual RSSI values. Is there a way to graph the Bluetooth? Another question, is there a way to graph the Bluetooth signal sent out by the beacons? Well, I'm not going to get into how one graphs it. That's just basic, mathematical visualization. You could put the values in Excel and plot them as a line or point charts. There's any number of ways to, but there, you have values, you have a value per observation. How you visualize it is up to you. All right. So I stated that you can represent PDFs and CDFs either parametrically by a closed form solution, a mathematical formula that therefore defines it perfectly, or you can measure it. You can get an empirical distribution. So the empirical distribution is what you get when you're actually collecting data. And so the most very basic version of this empirical distribution is what's called a histogram. And so histograms are just approximations of a variable's PDF. All right. So they're directly approximations of variable PDF. And if you sum these, i.e. integrate, you'll get the CDF. And they're basically collected, you construct them very simply. You collect lots of samples. Apologies. You divide the range of potential values into a series of discrete intervals or bins. Basically, does any given value fall between, -2 and 1 and -1, and then -1 and 0, and then 0 and 1, into discrete intervals, and you count how many samples fall into each bin. So what I have here on the left is I've taken 1,000 samples for each of 2 cases, and we'll go into those are. And I basically discretized this space between -80 and -20 into 1 dBm size bin. So I'm basically saying for the width of every single one of these bars is 1 dBm. And so, for example, let's use this big tall one right here. All right, this bin, if we follow it down, is probably, its edges of this bin are probably -45 to never mind, I can tell you exactly. This one is -40 to 39, and therefore this is -39 to 38. So this one is -38 to -37. This means that of the 1,000 samples I took, a little over maybe 95 of those samples fell between -30, sorry, I already lost track, -37 to -36, all right? Sorry, you're right, -43, my bad, I'm looking at backwards. Yeah, 40, 41, 40, 41, 42, -43, 44, okay? So minus 43, minus 44, and likewise for all the other bits. All right. What you'll notice is that I have two different distributions here. And basically what is this? Each one are histograms on one chart. One of these histograms is data I would have collected when the RSSI measurements were taken at distances less than 2 meters. And the other one is RSSI measurements I took when I was further than 2 meters apart. And so this goes to that question about how the different distributions shift, or how their means and variances may differ. And so you can see here, right, the idea here is that when they are within 2 meters, I would expect to get stronger RSSI values. So on average, the mean value should be larger or higher than when it was further than 2 meters apart, which is why you see these two separated by this, why the peak is here for the less than 2 meters, and the peak is further down the RSSI scale, or more negative on the RSSI scale for the greater than 2 meters. And this is fake data. This is just artificial data I created. But so they have identical variances, which is why their width is about the same. All right. Now, the important thing to notice is that I said that I generated this data artificially. I basically created a parametric distribution and I drew data from it. And so it's supposed to follow a true parametric distribution, specifically a normal distribution. So it should look like one of these curves, right? And you can sort of see that, but it's a little scruffy, it's not as clean. If your data actually follows a true parametric distribution, as you take more samples, it will start to resemble the true distribution more and more. So here I had only on the leftmost, I had 1,000 samples. In the middle, I have 10,000 samples, so 10 times more. And you can see things starting to smooth out, starting to look more like those normal. And over here, I have 100,000 samples. And now you can see it really is starting to look like those Gaussians, right? And it looked like those normal distributions almost perfectly, right? Still not perfect. You'd have to take 1 million samples or more to get to really look, almost exactly like a Gaussian. But these are the sort of distributions, or this is the sort of distribution you guys will be generating, not necessarily Gaussian, not necessarily normal, but by virtue of looking at the histogram of the data. And I'll show you more on that later. Let me answer some questions. Are we assuming that the frequency at each RSSI are Gaussian distributions? Is this always true? Is that an assumption we must have? No, you do not. There's no assumption that the RSSI is distributed Gaussianly or normally. That is just a convenient assumption I made for the sake of illustration. They may not follow a parametric distribution at all, right? There may be some weird lopsided, heavy-sided function that you're going to just have to empirically model, that it won't follow any nice known parametric distribution. But you should see if it, go on Wikipedia, go on Wolfram, and look up all the available distributions, all the known distributions, and see if your data resembles anything. Maybe it does. What is the best software for creating these types of graphs? So since I get a MATLAB license for free, I created these in MATLAB. But you can create these just as easily in Excel, create these just as easily in Matplotlib. There's plenty of, R, Octave, all of these things are capable of creating these sort of graphs. All right. So we've talked a little bit about, what is our task, this sort of detection problem, how does our data sort of look, from a probabilistic distribution standpoint. So let's jump into what is the sort of the actual the math of the test we're doing. So we're basically doing what's called a binary hypothesis test. We're basically deciding between two complementary hypotheses, one called the null hypothesis or H0, and the alternate hypothesis or H1. Typically, H0 is associated with the more commonly true hypothesis. Sorry, typo there. This is, in other words, this is how the world is normally. Usually that's the case because in most detection theory, the signal you're looking for, if it was omnipresent or super commonplace, you wouldn't really need to, be exerting a lot of effort to detect it. You'd be exerting a lot of effort to detect when it wasn't happening. So therefore, to sort of narrow the focus or to make it more clear as to what is the positive outcome or the positive declaration, H0 is declared the null, and it's associated with that more commonly true. And we'll go into some examples shortly. Deciding H1 is typically called the positive declaration because it's not the normal, right? When we make a declaration, it's usually a flag or a decision that something, we should take notice of something, that, do something after I declare H1. If I declare H0, go out about your business. Don't worry about it. Moving on. And usually the decision between these two is the outcome of some test on an observation or measurement. We have an observation or measurement in hand. We do some tests on it, or we make some, we do some math on it. We decide which of the hypotheses is true. And so, for example, on the fire alarm, that test is something like, do we detect or smell smoke? Smell being, I should put that in quotations because, it's a machine. It doesn't necessarily smell per se, but do we detect smoke, or heat or whatever is correlated with the fire? That is the test we're applying. Now, with the binary hypothesis test, there are 4 possible outcomes. The first pair are the correct decisions. When the truth is that for each, the truth is that if the null hypothesis is true, we declare that the null hypothesis, oops, and I made a typo here. These are all say H0. Apologies, I'll fix this in the slides later. But the first one should say decide H1 when H1 is true. And that is called the true positive. We've correctly declared that there's a positive detection. All right. And oh, my bad. I wrote it as, sorry. I wrote it correctly. I usually think about it differently. So we decide, or we accept H0 when H0 is true. That's called a true, forget it. Forget all this. Look at the graph. I'll fix this, my mistake. Look at the illustration. So on the top, and the columns correspond to the truth, and the rows correspond to the decision that's made. So when the truth is that H1 is true, and we declare H1 is true, that's called a true positive. That's, we've correctly made a declaration. The corollary to that is when H0 is true, and we declare H0, and that's called a true negative, right? We're saying that nothing has happened, and we're correct about that. It's the other 2 outcomes are the errors. For example, when H0 is true, but we say something has happened, that's called a false positive or a type 1 error. And the corollary to that is a false negative, when something actually did happen and H1 is true, but we declared nothing happened, i.e. H0 is declared. And we'll get into what these are for us later, but at the end of the day, you want to maximize the number of true positives and true negatives you're making and minimize the number of false positives of false negatives you're making. So I mentioned we had to make a test, all right? So in order to make a decision about which hypothesis to choose based on a measured sample, based on some measurement, sorry, I was just catching up with the questions. I don't understand. I'll answer that later. We need to do something with that measurement, right? So, just give you an example, right? Using the example of trying to find a person's voice in a crowd. the signal we're receiving is the auditory signal, right? Our ears here receive the signal, and then our brain does something with that signal to declare whether or not we actually hear the person or we don't hear the person. And that process, right, of doing something to our received signal is called a test. And it's basically just a predefined way to map all possible measurements onto the possible decisions. And don't mistake that wording as implying that you're doing a brute force mapping, that you know for every possible measurement what you explicitly say that this is the correct decision. If you were going to do that, then you would have to collect so much data and do so much additional work that it just wouldn't be viable. So we had to do some approximations. But the simplest or most common test is called a critical value or threshold test. And basically it's saying that we take the measurement and we say if that measurement value exceeds or is beyond a certain value, we reject H0, we declare H1, all right? So what you can see here is just a couple of ways to do that. And that's why beyond is in quotations, because it's not necessarily strictly greater than or equal to or something like that. But here's an example of a distribution, right, of a variable, of a measurement. And we're saying that we've drawn this threshold T alpha such that when the measurement we get T is greater than T alpha, we are going to reject H0 or declare H1. The other graphs show you different ways you could do this. You know, you could say instead of it being greater than T alpha, you could be less than minus T alpha. Or you could be what's called a two-sided test, you know, saying that if it's, you know, less than this threshold and greater than this threshold, we're going to reject. And so we only accept H0 in the center here, and we declare H1 outside of there. And so there are lots, test statistics are just basically intermediate values you use to compute the test. You know, the test statistic could be as direct as the sample itself, right? That RSSI measurement directly, but it could be more complicated. It could be, I take multiple RSSI measurements together and I do something with them together, for example, average them together. And so the average of multiple tests, of multiple samples is my test statistic, all right? And then I apply a test to that statistic. All right, and then there's a lot of other standard types. There's z-test, t-test, chi-squared, et cetera, et cetera. You know, if you want to get really fancy, you could, you know, create a machine learning algorithm that did something to your RSSI measurements and produced a confidence value. And then you take that confidence value and you apply some tests to it. I only declare that, you know, I reject H0 if the confidence is less than this value, because my algorithm is not confident. And so the bottom line is tests do not need to be based on statistics at all. I said it was just a way to map measurements onto decisions. You don't have to create, you know, actual statistics. You can just sort of say like, I'm just going to measure 10 samples and gonna randomly pick, you know, the worst, you know, maybe the most naive test you could do in a binary hypothesis test is flip a coin. You know, you collect all this data, you measure it, but then you don't use it at all. You just say, I'm gonna flip a coin and if it's heads, I say H0, if it's tails, I say H1. You know, I'm not using any of the data I actually collected, but it's still a perfectly valid test. It's just not using a test statistic. All right. Let me catch up with some of the questions here. I think I answered the normal distribution question. How can we experiment if something has COVID or not? I can look at the RSSI values in devices, but that would use us without knowing if it. So that's a higher level question, right? If you have to go back to the whole PACT concept, so I'm not going to answer that now. Go watch previous lectures. That's a much earlier decision. That's a much earlier topic, so I'm not going to answer that one. How can we make something that will detect in binary file like the fire alarm for the purpose of using beacons? I guess I don't understand what you mean by binary file. There's no binary files involved. Okay, I think I got all the questions. Yeah. Okay. So moving on. So let's wrap all this up together a little bit and look at this sort of like in a probabilistic view. All right. So we can actually sort of visualize everything we're doing sort of compactly in one nice little graph. So first, let's just talk through this graph and don't worry about the words on the left for now. So what we've got here is our distributions, our two different distributions collected under each of our hypotheses, where H0, or the null hypothesis, is that two people are more than 2 meters apart. And H1, or the alternate hypothesis, is that they are within 2 meters, all right? And so you can see here, I have two different distributions, H0 in orange and H1 in blue. And you can see, unlike my previous examples, they look somewhat fairly different from each other. H1 is much more compact. It has a higher mean value, while H0 is much more spread out with a lower mean value, right? We expect lower RSSI values for the H0 hypothesis, but we also expect a lot more variability because, greater than 2 meters represents everything, right? It's not just 2 meters to 3 meters, it's 2 meters to 10 meters or 2 meters to 30 meters, whatever it may be. Well, less than 2 meters is 2 meters to 0 meters. So it's expected to be more compact at some aspect. And so the test I've chosen to do here is that critical value or threshold test, where I'm just going to draw a line, or sorry, let me back up. It's the critical value or threshold test. And the test statistic I'm going to use is just the RSSI value. I'm just going to look at the RSSI value. I'm going to say if it's greater than some value, I'm going to say it's H1. If it's less than some value, I'm going to say it's H0. And so that's what that vertical dashed line is. And so if we draw this dashed line, and I've just picked a place, to the right of that, I declare H1, and to the left of that, I declare H0. Now once we have all this, we can start to see what are the errors I'm going to be making with this particular test, right? So remember, the type 1 error is the fraction of errors of H0 that are incorrectly declared to be H1, all right? So these are false positives, all right? And so you can see here, it is the amount of the orange histogram that is to the right of the dashed line. So you can see I'm going to make this amount of errors. On the other side, the type 2 errors are the false negatives, right? Where the truth is that the truth is H1, but I declare H0, is this fraction of the blue histogram that's going to cause type 2 errors, right? And you can see if I shift this line, maybe if I shift the line to the right, the critical value to the right, I'll make fewer type 1 errors, but I will make more type 2 errors. And vice versa. Shift it to the left, I'll make fewer type 2 errors, but I'll make more type 1 errors. And so this is a trade, right? There's no free lunch here. You're going to have to figure out what is the right trade. Now, this construction only describes how things would nominally change. It's not perfect because, again, this is empirically collected data, right? You may not have collected enough data. You may not have collected the right data that to represent the real distribution, right? The distribution may not actually be Gaussian. It may look Gaussian, but maybe it's not really Gaussian. At the end of the day, these are all approximations. These are best guesses. These are best estimates. So always take that with a grain of salt. How would we determine where to put the critical value? Well, that is part of the exploration. You have to look at how your data, how many errors am I making? What types of errors? When I choose this critical value versus that critical value. And we'll get into some of that in a second. So, So let's talk about some performance metrics. I'm just going to speed things up a little bit because there's a really good Wikipedia article about this, but the graphs tell the whole story, or the images tell the whole story. So bottom line is you always want to maximize correct decisions and minimize incorrect decisions. You always want to do that. Doesn't matter. But if you only look at type 1 and type 2 errors, you may not actually be correctly quantifying the true cost of your approach. And specifically, some errors are more costly than others, depending on your context. So for example, if you're going in to get like a cancer screen, if you're incorrectly declared to be free of cancer, but you actually have cancer, right? You've missed a treatment opportunity, right? So that's a false negative, right? And so in that sense, false negatives are much more costly than false positives because you would like to err on the side of caution. However, on the other side, from like more a security standpoint, getting into your phone using your face, you would probably want to err on the side of allowing more false negatives. In other words, not letting people into your phone than allowing false positives, letting people into your phone. All right. And so you had to strike that balance, right? Which one, depending on the application, makes most sense for you. And you have to think about downstream effects, because usually when a positive is declared, they kick off other things, right? So in the COVID case, right, if you incorrectly declare a false positive, if you declare a false positive, then you may end up isolating or quarantining a lot of people who don't need to be quarantined. On the other hand, a false negative means that the virus may spread some more. And striking that balance is not necessarily your responsibility, but the responsibility of decision policymakers about where is the right trade, because it's a public policy health decision. I'll skip over the rest of these, but this goes into why there's some additional metrics that you may want to look at: precision, recall, sensitivity, specificity. And these are some really good Wikipedia articles that'll explain all that. We're running out of time. Okay, so here is how you're going to help you decide where to put that critical value if you're using that approach. Again, critical value is the simplest test you could do. It is not necessarily the test you have to do or the test you should do. It's just a decent starting point and something to try. So what we have here is what's called receiver operating curve. And this is a tried and true tool for detection theory, detection characterization. What you have here on the x-axis is the false positive rate, all right? So those are false positives. And on the y-axis is the true positive rate. The easier way to think about this is the hit ratio when we are correctly declared H1, and here is when we incorrectly declared H1, all right? And so if you think about where you want to operate on this graph, you want to operate way up here in the left corner, right? You want to correctly declare everything that's H1, and you want to reject everything that is H0. So you want to be here. You want to be perfectly declaring all H1 and perfectly rejecting all of H0. However, you're very rarely in that corner. You're more than likely somewhere else on this in this graph. Now, the place to start is actually here in the center with this random guess line. If you look at this line, what this is basically saying is that for any given point, right, if I'm declaring, right, 40% of the time that 40% of the detections I'm making, I'm correct on, then I'm also incorrectly declaring that 40% of negative cases, the H0, are also positive. And that's what we call the random guess line, because at this point, it's basically a 50-50 guess, right? You could flip a coin and get the same result. If you're below this line, you're actually doing worse than random guessing. You're actually making more false positives than you're making true positives. Now, based on your based on the nature of your test, right, you may have parameters to pick. So for example, the critical value. So as I change the critical value, I may get different performance points. And that's what these little dots are, right? So if I chose a certain critical value, I may have very low false positive rate, but I may be missing a lot of positive, or have a very low true positive rate. And so as I change the critical value, I get more true positives, but I'm letting in more false positives. As you can see here, as I go up and up, I'm getting better true positive rate, but I'm letting in more false positives. And so picking that critical value is about where on this curve do I want to be, right? Do I want to make sure I'm correctly detecting my true positives and I'm rejecting false positives? But where on this line do I want to be? And so as you change your test, the shape of the curve will also change, right? It'll end up being, as you improve your test, you'll shoot up this curve very quickly, getting to some, decent point where it looks like, oh, this is pretty good performance, but then it's going to be very hard to move it into this corner, because this is where the threshold or the critical value is not going to have as much effect, because it's done most of its work here. So that a good example would that be here, right? Is if I drew the line over here, like at -50, I'm going to get my true positives, but I'm going to have a lot of misses. All right. And so, that's a pretty good starting point. But as I move the line over, eventually I'm going to get some false positives, and I'm going to start missing some of my true positives. So again, running out of time, so I got to get to kind of the meat, or how this relates to PiPact. So the PACT, how this relates to PACT first. So again, the fundamental PACT premise is to detect when two people are too close for too long, right? Has been abbreviated TCTL, right? So, and the task at hand for PACT is how to devise and evaluate a test that maximizes performance and minimizes errors, right? So we want to be, correctly detecting all the people who have COVID, or associating when two people, not detecting when people have COVID, associating when people are too close together, and ensuring that we don't make those declarations when they're actually far apart. All right, and we can map this to this binary hypothesis test. So where H0 are people are not too close, too long, as H0, and to also where an H1 would be people are too close for too long. All right, and the test is some function of our RSSI measurements. And again, that's a lot of the research that's being done. And there's so many different types of tests that you can do. Again, we talked about a few of these. You can threshold on a single RSSI measurement. You can do a threshold on an average of number of measurements. You can do, say I want to collect n measurements, and at least if m of them exceed a threshold, I'll declare a positive or an H1. You could threshold a weighted average of n measurements. You could do something where you have another sensor that says this, measurement 1 was a good measurement because, the two devices are facing each other. Therefore, I don't have artificial loss. Or some other values. All right. And here, this is directly taken from the Impact Conference slides. And you can see here that they're showing a very similar graph that I did, where they have two different curves where they say, oh, there's the manual tracing curve, Here's some semi-automated algorithm, and here's some better algorithm, right, that does better. And somebody asked a question is what causes a change in the test line? What causes a change in the test line is actually a change in the type of test you're doing, right? For example, these tests I've described below, each one of these would be a different line, right? They would have different types of performance, right? How that curve manifests is how the different parameters in each of those tests. So, for the first test, the threshold of single RSSI measurement, the parameter you have is the critical value. That's what would slide you along this blue line, for example, if that blue line was this test. And then the next test I try is averaging M measurements, right? So now maybe I have two parameters. One is what is the value of M? How many measurements am I averaging? And what is the threshold? And so that may take me to this green line, and every point on the green line is some different combination of the parameters. And then there could be another line, which is my third option, which is M and N, M of N. So now I have three parameters. I have M, N, and a threshold. All right. And then so you can go, so they're not all expected to follow the same line, right? They all are different by virtue of the way they are actually doing their math. All right. So some PiPact recommendations. All right. So again, I know there's a lot of info, but like I said, these are semesters, if not years of material crammed. The very glaze, the very thinnest layer of this for you guys. So some recommendations. So assuming you're doing something where you can do a binary hypothesis test, some of you aren't even looking at the actual detection part, which is fine. But if you are, start with a very simple single measurement critical value test. So collect one measurement and apply a critical value threshold test to it. And so what you should do is you collect a set of data for each of your hypotheses, like we did, like this represents, right? Collect, data for your H0 and collect data for your H1. And then visualize it using histograms. Determine a critical value threshold that seems to separate your hypothesis with minimal error. Compute and log the correct or incorrect decision rates and performance metrics. And then vary that threshold and repeat step 4. And by going through the cycle of varying the threshold, figuring out your metrics and logging them, you'll be able to create that RSC, create that curve. And then visualize that RSC curve and see how much improvement is left. How close to this corner are you? If you're like right above random guess, then you got some work to do. If you're below random guess, that was a bad test. Get rid of it. A bad test statistic. All right. It's not likely to be a bad test statistic, but it's like maybe it was a bad test. But see how much improvement you need to make, or you have opportunity to make. After you do even this simple thing, you can start to experiment with how to construct more complicated tests. All right, and separation of data. So the most obvious thing is to use multiple measurements. For example, averages or M of N. And I'll discuss M of N in Piazza later if people are interested, but not right now. And you also want to consider creating separate distributions and tests for distinct scenarios. So, the distribution I model here may only be for the data I collect inside, while I have another pair of distributions for data I collect outside. And I have two different tests, one for inside and one for outside, and they just represent different ways of tackling the problem. And that might simplify or make your overall algorithm more effective because, if I was to throw all the data together, right, I may get distributions that aren't, that are super overlapped, that I'm going to have lots of error, and it's not going to be very effective. Okay. And so if you look at the life cycle of this whole thing, right, it's fairly straightforward. You're going to collect data. You should create distributions. create some sort of test based on your distribution you see. It doesn't have to be this critical value or threshold. And then you're going to evaluate that test, right? You're going to see how many true positives have, true negatives, what sort of errors you have. And then you're going to generate those metrics, right? You're going to generate those metrics so that you see where you are in the art of the possible. And then based on where you are, you'll decide whether what you need to change, right? If you're making a lot of, if you're getting a lot of true positives, your true positive rate is very high, but you're getting a lot of false positives, you may want to think about, the threshold value, or you may want to change, you may want to change the number of samples you're using. You may want to filter the data. There's so many things you can do. And again, independent project. I'm not here to give you a formula. All right. We're nearly at the end, but I'm going to try to answer the last remaining questions. So I think I answered how would we determine where to put the critical value. Well, you determine it a little bit by trial and error. It's mostly just to do with the simple fact that you pick a point and you observe what the performance is, and then you shift where that point is, and then you see what the new performance is, and if it gets better, then the new critical value is better. Gets worse, the new critical value is worse. I answered what causes the change in the test line. It just has to do with the nature of the test, right? Different tests are going to produce different test lines. You will see that for yourself. You'll definitely see that as you start to go from using a single measurement to using multiple measurements, if you so choose to. I highly recommend you try things like that. How do we produce graphs like this for a theory we might have? Well, it depends on what you mean by theory. This whole process, okay, is about really evaluating an approach, right? Your theory was back when you generated your hypothesis, right? Or you said that I have a certain hypothesis that, hypothesis H0 and H1. You, based on that hypotheses, you collected data that will allow you to explore that hypothesis. So, if your hypotheses are within 2 meters and outside of 2 meters, or if your hypotheses are inside, outside, or your hypotheses are obstruction, no obstructions, you will collect that data and you start to generate these graphs based on the data you collect. And then based on the conclusions you make, you refine the data and you refine the hypotheses or the test or all of the above, and you go through the cycle again. Okay. The graph about how many, this is not, I don't know what this question is asking. The graph about how many positives versus negatives. I'm not sure what that means. If the question, so whoever asked that question, if you want to re-ask it, maybe a little bit differently or more completely, would it be recommended to use density estimators to approximate functions from data? Yeah, absolutely, you can definitely use density estimators. Again, word of caution, if you're using a density estimator associated or anchored in a parametric distribution, for example, if you are trying to use a density estimator as approximating a normal distribution, you are inherently assuming your data follows a normal distribution. And whether in reality it does or does not is to be seen. So do that with a grain of salt. It's a perfectly fine place to start. It's quote unquote for free outside of your time and effort, but you just want to take caution with making too many assumptions about using density estimators that sort of make some initial assumptions. Now, if you do something like a partisan density estimator that just tries to fill in the gaps, those are generally fine. How do we produce the graphs that you had for a number of positives versus the number of negatives? Put our line into it based on data. Okay. So they're very simple. Okay, so for this graph, this true positive rate, actually, let's go back here. All right, I'll explain this real quickly, and then well, that'll be the end of the lecture. So what this graph is showing is all the possible samples you got here. All right, and the space is divided into basically things that you declare, or sorry, I had to remind myself here. These are true positives, these are false. Okay, so this space, what's inside the circle are actual positive or true, like H1 declarations or H1 values, right? These are positives. What's outside of here are negatives, okay? And divided down the center is basically our decision space. So on the left side, we declare it's a positive. On the right side, we declare it's a negative. So as you can see here, inside the circle and on the left is when we correctly declare it's a positive declaration. So that's a true positive. Inside the circle on the right is when we've incorrectly declared something as being negative, right? So those are false positives. And then the same is true for outside the circle. When something is actually positive, when something is actually negative, what we declared as positive, and when something is actually negative and we correctly declare it as negative, all right? And basically to generate those curves, all you're doing is to count of all your data you collected, what fraction is inside this section relative to everything that is here. So that's what's called the true positive rate, all right? What fraction of all the positive samples did I correctly declare as being truly positive? The false positive rate is what sample of the negative samples, or what fraction of the truly negative samples did I incorrectly declare as positive samples? All right, and that's why this graph goes from 0 to 1. These are fractions or rates. All right. So that's, you could also replace, instead of rates, you could replace those with just counts. How many samples did I correctly declare positive? And how many samples did I incorrectly declare positive? The scaling of this changes. It won't be square, or 1 to 1, but they represent the same information, or they have, the scaling factors on each of these axes may be different. Okay. And with that, I'm going to declare this lecture closed. I know it's a lot of information. I'm going to highlight, again, there's a reason why almost every single one of these pages has references at the bottom. They're there for you to go read and learn and try. And there's no shortage of tutorials online about how to do particularly binary hypothesis testing. No shortage of Jupyter notebooks, no shortage of any of these things. Again, you guys got to do some independent research to understand, but start with this. Start with these basic 6 steps. If you can go from collecting data to creating something that looks like this graph, this ROC curve, then you know how to do this process, all right? And we're here to help. And I'm sorry, I haven't been on Piazza lately. I know there's a lot of stuff up there, but even we need holidays sometimes, so we got to take them. So enjoy. I hope you guys had a good July 4th. And for those of you, getting into Beerworks